Welcome everyone. Today, we'll be presenting an overview of inline inspection, or ILI, which is a critical method for maintaining pipeline integrity. We'll explore its importance, tools, workflow, and future trends, enhancing pipeline integrity through inline inspection or ILI. Introduction to pipeline inline inspection or ILI. ILI involves running inspection tools through pipelines to assess their condition without interrupting operations. These tools, often called PIGs, collect data on internal defects and structural issues. Key point number 1 of pipeline inline inspection or ILI is a non-destructive testing method for pipelines. Inline inspection or ILI allows engineers to assess the internal condition of pipelines without cutting, damaging, or interrupting their operation. It uses advanced sensors and technologies embedded in inspection tools or PIGs that travel through the pipeline. This means we can inspect the pipeline's condition without taking it out of service. It's a safe and efficient way to monitor pipeline health, especially for long-distance or buried pipelines. Key point number 2 of pipeline inline inspection or ILI is ILI, also known as smart pigging. The term smart pigging refers to the use of intelligent inspection tools called PIGs that are equipped with sensors, data storage, and sometimes GPS. These tools collect detailed information as they move through the pipeline. And the key point number 3 of pipeline inline inspection or ILI is enabled to detect corrosion, cracks, and geometric anomalies. ILI tools can identify a wide range of defects including corrosion, such as metal loss due to chemical reactions. Corrosion is one of the most common threats to pipeline integrity. Cracks, such as stress-related or fatigue-induced fractures. Cracks can lead to catastrophic failures if undetected. Geometric anomalies, such as dents, ovalities, and weld misalignments that may affect flow or structural integrity. Geometric anomalies may not cause immediate issues but can affect flow dynamics and stress distribution. ILI helps us catch all these early. Why pipeline inline inspection or ILI matters. ILI helps us identify potential issues before they become critical. It's not just about safety. It's also about cost efficiency and regulatory compliance. Early detection means fewer shutdowns and better planning. Key point number 1 of why pipeline inline inspection or ILI matters is ILI helps to prevent pipeline failures and environmental hazards. ILI helps detect early signs of corrosion, cracks, or deformation that could lead to leaks or ruptures. Preventing these failures protects the environment, avoids costly cleanups, and ensures public safety. Pipeline failures can be catastrophic, causing explosions, oil spills, or gas leaks. ILI helps us catch problems early, reducing the risk of such incidents. It's a key part of our safety and environmental protection strategy. Key point number 2 of why pipeline inline inspection or ILI matters is ILI helps to ensure pipeline integrity programs compliance with safety regulations. Regulatory bodies like PHMSA, API, and local authorities require regular integrity assessments. ILI provides documented evidence of pipeline condition, helping operators meet legal and industry standards. Governments and industry bodies mandate regular inspections. ILI provides the data we need to demonstrate compliance. It also helps us avoid fines, shutdowns, and reputational damage. Key point number 2 of why pipeline inline inspection or ILI matters is ILI supports predictive maintenance and asset management. ILI data allows operators to forecast potential issues and schedule maintenance before failures occur. This shifts maintenance from reactive to proactive, optimizing resources and extending asset life. Instead of waiting for something to break, we use ILI data to predict when and where issues might arise. This allows us to plan maintenance efficiently, reduce downtime, and make smarter investment decisions in pipeline infrastructure. Types of pipeline inline inspection or ILI tools. Different tools serve different purposes. MFL is great for corrosion to detect metal loss. Ultrasonic testing or UT for measures wall thickness and cracks. Caliper tools for geometry. This caliper tools used to identify dents and deformations. An electromagnetic acoustic transducer or EMAT and eddy current for advanced for crack detection. Choosing the right tool depends on pipeline material, diameter, and inspection goals. This table types of pipeline inline inspection or ILI tools below summarizes the main types of ILI tools. Each has its strengths and limitations, so tool selection depends on pipeline material, defect types, and inspection goals. For tool type is MFL or magnetic flux leakage, it is enabled to detect the defect that is occur in the pipeline with the maximum wall thickness is, up to 31 mm, able to detect defects such as, metal loss and corrosion. This measurement type is called indirect or magnetic flux leakage. Medium requirement to conduct this inspection is, dry or liquid, material. Compatibility to measure or detect is, ferromagnetic only. The advantages of this MFL or magnetic flux leakage inspection method is, fast, well established and good for corrosion detection. The limitations of this MFL or magnetic flux leakage inspection method is, limited crack detection, saturation issues in thick walls. For tool type is UT or ultrasonic testing, it is enabled to detect the defect that is occur in the pipeline with the maximum wall thickness is 40 mm and above, able to detect defects such as wall thickness, cracks, and laminations. This measurement type is called direct or ultrasonic echo. Medium requirement to conduct this inspection is, requires liquid coolant. Material compatibility to measure or detect is, ferrous non-ferrous. The advantages of this UT or ultrasonic testing. Inspection method is, high accuracy, direct sizing. The limitations of this UT or ultrasonic testing inspection method is, slower, needs clean pipe and liquid. For tool type is caliper tool, it is not able to detect the defect that is occur in the pipeline's wall thickness. It is able to detect defects such as, dents, ovality, deformation. This measurement type is called, mechanical contact. Medium requirement to conduct this inspection is, any medium. Material compatibility to measure or detect is, all materials. The advantages of this caliper tool inspection method is, simple, detects geometric anomalies. The limitations of this caliper tool inspection method is, cannot detect corrosion or cracks. For tool type is EMAT or electromagnetic acoustic transducer, it is enabled to detect the defect that is occur in the pipeline with the maximum wall thickness is, up to 25 mm and up to 30 mm, they varies by setup, able to detect defects such as, cracks, SCC, laminations. This measurement type is called, electromagnetic ultrasonic. Medium requirement to conduct this inspection is, no coolant needed. Material compatibility to measure or detect is, ferrous non-ferrous. The advantages of this EMAT or electromagnetic acoustic transducer inspection method is, non-contact, good for SCC welds. The limitations of this EMAT or electromagnetic acoustic transducer inspection method is, lower resolution, evolving tech. For tool type is eddy current or EC, it is enabled to detect the defect that is occur in the pipeline with the maximum wall thickness is, up to 15% of wall thickness, able to detect defects such as, surface cracks, corrosion, material changes. This measurement type is called, electromagnetic impedance. Medium requirement to conduct this inspection is, dry or liquid. Material compatibility to measure or detect is, conductive materials. The advantages of this eddy current or EC inspection method is, sensitive to surface flaws, no coolant. The limitations of this eddy current or EC inspection method is, limited depth penetration, not ideal for thick walls. According to this table of tools, here are the tips to select the tools. The first is, use MFL for fast, large-scale corrosion detection in ferrous pipelines. The second is, use UT for high-resolution wall thickness and crack detection in liquid pipelines. The third is, use caliper for geometry surveys and deformation analysis. The fourth is, use EMAT where couplants are impractical or stress corrosion cracking or SCC is a concern. And the fifth is, use eddy current for surface flaw detection in conductive materials, especially in thinner walls. Pipeline inline inspection or ILI simple workflow. The ILI process starts with planning and ends with actionable insights. Each step is crucial, from selecting the right pig to interpreting the data and deciding on repairs or monitoring. Workflow step number 1. Pre-inspection planning. Define inspection objectives, review pipeline specifications, assess risks, and schedule operations. Includes coordination with operations and safety teams. This is a critical phase where we define what we want to achieve, whether it's detecting corrosion, verifying pipeline geometry, or assessing integrity after an incident. We also gather pipeline specs like diameter, material, and operating conditions. Coordination with operations ensures minimal disruption. Workflow step number 2. Tool selection and launch. Choose appropriate ILI tool based on pipeline material, diameter, and expected defects. Launch the tool from a PIG launcher and monitor its progress. Tool selection depends on the type of defects we expect. For example, MFL for corrosion, UT for cracks. Once selected, the tool is inserted into the pipeline via a PIG launcher. We monitor its movement to ensure it travels at optimal speed and collects quality data. Workflow step number 3. Data acquisition during run. The tool travels through the pipeline, collecting data on wall thickness, geometry, and anomalies. Speed and pressure are controlled to ensure data quality. As the PIG moves through the pipeline, sensors collect data continuously. It's important to maintain stable flow conditions. Too fast or too slow can affect data accuracy. The tool may also record GPS or odometer data for precise location mapping. Workflow step number 4. Data analysis and reporting. Raw data is processed using specialized software. Anomalies are identified, classified by severity, and mapped to pipeline locations. After the run, data is downloaded and analyzed. This involves filtering noise, identifying anomalies, and classifying them by severity. Reports include defect locations, types, and recommended actions. This step often takes days to weeks depending on data complexity. Workflow step number 5. Remediation and follow-up. Based on findings, maintenance actions are planned, such as repairs, re-inspections, or monitoring. Reports are archived for compliance and future reference. Based on the report, we decide on actions, whether immediate repairs, further inspections, or monitoring. This step ensures the pipeline remains safe and compliant. Documentation is also important for audits and future reference. Detail step process. Step 1. Start ILI process. Initiate the inspection program based on regulatory requirements, risk assessment, or operational needs. Step 2. Define inspection objectives. Determine what needs to be detected such as corrosion, cracks, deformation, and the required resolution. Step 3. Assess pipeline pigability. Evaluate whether the pipeline can accommodate ILI tools such as bends, valves, diameter changes. Step 4. Select ILI tool type. Choose the appropriate technology, MFL or magnetic flux leakage for metal loss, UT or ultrasonic testing for wall thickness, EMAT or electromagnetic acoustic transducer for cracks, caliper or geometry for dents and ovality. Step 5. Clean and prepare pipeline. Use cleaning pigs to remove debris and ensure smooth tool passage. Step 6. Run ILI tool through pipeline, launch and receive the tool, ensuring proper data collection during the run. Step 7. Retrieve and analyze data. Download and process data using specialized software and trained analysts. Step 8. Identify and classify anomalies. Detect and categorize defects based on size, type, and location. Step 9. Perform integrity assessment. Evaluate the impact of anomalies using standards such as API 579 or ASME B31G. Step 10. Recommend actions and document and report results. Suggest monitoring, repair, or re-inspection based on severity and risk. Compile findings into a formal report for stakeholders and regulatory bodies. Step 11. End process. Conclude the ILI cycle and integrate results into the integrity management system. Pipeline inline inspection or ILI data analysis and reporting. After the PIG run, data is analyzed using specialized software. We look for patterns, classify defects, and generate reports that help prioritize maintenance. Accuracy here is key to effective decision-making. Key number 1. Raw data is processed into actionable insights. Once the pig run is complete, the data is extracted and processed using specialized software. This step involves filtering out irrelevant signals, aligning data with pipeline geometry, and converting sensor readings into measurable parameters like wall thickness or metal loss. In other words, after the ILI tool completes its run, the collected data, often terabytes of sensor readings, is downloaded and cleaned. Signal noise is removed, and the data is calibrated to match pipeline specifications. This transforms raw sensor outputs into meaningful engineering data. Key number 2. Anomalies are classified by severity. Not all defects are equally dangerous. We use algorithms and engineering judgment to classify anomalies. For example, a shallow dent may be low risk, while a deep crack near a weld could be critical. This classification helps us focus resources where they're needed most. Detected anomalies such as corrosion, cracks, or dents are categorized based on size, depth, location, and proximity to welds or stress points. Severity levels such as minor, moderate, and critical help prioritize maintenance actions. And key number 3. Reports guide maintenance decisions. The final deliverable is a comprehensive report. It includes visual representations of the pipeline, defect summaries, and recommended actions. These reports are essential for planning maintenance, budgeting, and ensuring compliance with safety standards. In other words, the final report includes detailed maps of defect locations, severity ratings, and recommended actions. These reports are used by integrity teams to plan repairs, schedule re-inspections, or monitor specific areas. They also serve as documentation for audits and regulatory compliance. Challenges in pipeline inline inspection or ILI. ILI isn't without challenges. Some pipelines are hard to inspect due to bends or diameter changes. Data can be complex, and remote locations add logistical hurdles. These are areas where innovation is ongoing. Challenges number 1. Tool compatibility with pipeline geometry. Not all pipelines are piggable. Sharp bends, diameter changes, and complex fittings can obstruct the tool or distort data. In such cases, we may need to modify the pipeline or use tethered or robotic inspection tools. Pipelines with tight bends, varying diameters, Ts, or unbarred valves can be difficult or impossible for ILI tools to navigate. This limits inspection coverage and may require custom tool design or alternative methods. Challenges number 2. Data interpretation complexity. The volume of data from a single ILI run can be overwhelming. Analysts must filter out noise, calibrate readings, and interpret signals accurately. Misinterpretation can lead to missed defects or unnecessary repairs. ILI tools generate massive datasets that require expert analysis. Differentiating between true anomalies and signal noise can be challenging, especially in older pipelines with complex histories or codings. Challenges number 3. Accessibility in remote or offshore locations. Deploying ILI tools in remote jungles, deserts, or offshore rigs requires careful planning. Weather, transport, and safety protocols can delay operations and increase costs. Sometimes, inspection windows are very narrow. Launching and receiving ILI tools in remote areas or offshore platforms involves logistical challenges, including transportation, safety risks, and limited infrastructure. These factors can increase inspection costs and time. Challenges number 4. Operational constraints during inspection. ILI tools need consistent flow and pressure to function properly. Sudden changes can cause the tool to stall, speed up, or lose data. Coordinating with operations to maintain these conditions is a common challenge. ILI requires stable flow conditions and controlled pressure. Any fluctuation during the run can affect data quality or cause tool malfunction. Coordinating with operations to maintain ideal conditions is often difficult. And challenges number 5. Limitations in detecting certain defects. Each tool has its strengths and weaknesses. For example, MFL is great for corrosion but not for cracks. UT is precise but slower and needs couplant. Understanding these limitations helps us choose the right combination of tools. Some tools may miss specific defect types, for example MFL may not detect tight cracks, and UT may struggle with rough internal surfaces. No single tool can detect all anomalies, so multi-tool strategies are often needed. Future trends in pipeline inline inspection or ILI. The future of ILI is exciting. AI is improving defect detection, and real-time data allows quicker decisions. Digital twins can simulate pipeline behavior, enhancing predictive maintenance strategies. Trend number 1. AI and machine learning in anomaly detection. Traditionally, data analysis was manual and time-consuming. Now, AI can scan thousands of data points in seconds, identify patterns, and flag anomalies with high precision. This not only speeds up reporting but also enhances reliability by reducing human bias. Advanced algorithms are being trained to automatically detect and classify pipeline anomalies from ILI data. These systems can learn from historical inspection data to improve accuracy and reduce human error. They also help prioritize defects based on risk models. Trend number 2. Real-time data transmission. Instead of waiting days or weeks for post-run analysis, some modern pigs can transmit data as they move through the pipeline. This is especially useful in critical infrastructure or emergency inspections, where time is of the essence. Emerging ILI tools are equipped with wireless communication capabilities that allow data to be transmitted in real time during the inspection run. This enables immediate anomaly detection, faster decision-making, and reduced downtime. And trend number 3. Integration with digital twin technology. Digital twins allow us to simulate pipeline performance using real-world data. By integrating ILI results, we can visualize stress points, predict corrosion growth, and test repair strategies virtually before applying them in the field. This leads to smarter, data-driven decisions. Digital twins are virtual replicas of physical assets. ILI data can be fed into these models to simulate pipeline behavior under various conditions. This helps predict future failures, optimize maintenance schedules, and improve asset lifecycle management. Conclusion in this pipeline inline inspection or ILI presentation. Number 1. ILI is vital for safe, efficient pipeline operations, and number 2. Continuous innovation is improving accuracy and reliability. ILI is a cornerstone of pipeline integrity management. It's evolving rapidly, and staying updated is essential. Top 10 frequently answers and questions about ILI inspection. Question number 1. What is inline inspection or ILI? And the answer is, ILI is a non-destructive method used to assess the internal condition of pipelines by running inspection tools or smart pigs through them to detect defects such as corrosion, cracks, and deformations. Question number 2. What types of defects can ILI detect? And the answer is, ILI can detect metal loss, for example, corrosion, pitting, cracks, for example, longitudinal, transverse, SCC, geometric anomalies, for example, dents, ovalities, weld misalignments, coating disbondment, for example, with advanced tools. Question number 3. What are the main types of ILI tools? And the answer is, magnetic flux leakage or MFL for corrosion detection, ultrasonic testing or UT for wall thickness and cracks detection. Caliper tools for geometry detection, IMAT and eddy current for advanced crack detection. Question number 4. How often should pipelines undergo ILI? And the answer is, frequency depends on pipeline age, material, product transported, and regulatory requirements. Typically, inspections are done every 3 to 5 years, or more frequently for high-risk lines. Question number 5. Is ILI suitable for all pipelines? And the answer is, not always. ILI tools require certain pipeline conditions, for example, piggable design, minimum diameter, and flow rate. Unpiggable pipelines may need alternative methods like ECDA or hydrotesting. Question number 6. What happens after an ILI run? And the answer is, data is downloaded, cleaned, and analyzed. Anomalies are classified by severity, and a report is generated to guide maintenance, repairs, or further inspections. Question number 7. How accurate is ILI data? and the answer is, accuracy depends on tool type, pipeline conditions, and calibration. MFL tools typically detect metal loss with more or less than 10% accuracy, while UT tools offer higher precision for wall thickness. Question number 8. Can ILI detect external corrosion? And the answer is, ILI primarily detects internal conditions. However, some tools, like UT and EMAT, can infer external corrosion if wall thinning is detected and matched with location data. Question number 9. What are the limitations of ILI? And the answer is, limited access in complex pipeline geometries, data interpretation complexity. Not all tools work on non-metallic or coated pipelines, requires flow and pressure control during inspection. Question number 10. What are the latest innovations in ILI? And the answer is, AI-based anomaly detection, real-time data transmission, integration with digital twins, compact tools for small diameter or challenging pipelines. Thank you.